Floor is yours.
Okay. Hello, everyone. It's very nice to be here, and thank you to the organizers for giving me the opportunity to talk about my work. I'm here as a substitute for Yuping An, who couldn't be here, unfortunately. And I'm going to be talking about a work, an ongoing work that we are doing with Yuping, with Blaise, who is in the audience, Lily, and Michael Stances. Yeah, so it's going to be quite different from the previous talks, but I will also have some notes. Okay, so let me just first motivate the two sides, or the two approaches that we are going to use in order to study the system that we are interested in. So we are going to use holography and hydrodynamics. So first of all, why study hydrodynamics? Basically, hydrodynamics is a universal theory that describes the late-time, long wavelength behavior of thermalizing systems, which should be chaotic and with many degrees of freedom in general. It's very universal, as I said. It can be applied to the early universe. It can be applied to high-temperature superconductors, strange metals, and many other systems. Now, why use holography on the other side? So, holography is a theoretical framework for strongly interacting materials without quasi-particles. So, you can see that there is already an overlap with the system that hydrodynamics can study. Using holography, we can have analytic results, for example, in a derivative expansion, in special derivatives. There have been derived some universal bound for transport coefficients of hydrodynamic theories. And most importantly, it's much easier to do numerics than in strongly coupled QFTs. So the system that we are going to study is basically a superfluid with a large number of mobile vortices. This can be motivated by the fact that we know, for example, that in superconductors, if we have a magnetic field, this creates vortices. They can be arranged in a lattice, but in other cases, they can be like free and move around. So we are just going to consider a simple version of that, which is just a superfluid. So we will have a global U1 symmetry. And in general, we can consider this as a vortex fluid. This has been analyzed in the past, but mainly at 0 temperature, so without dissipation. And we want to consider this system at final temperature here. A significant development was when people understood that superfluids have some emergent, low energy emergent symmetries, which are of the higher form type. And this basically, and the vortices are currents, are defects, which explicitly break these higher form symmetries. This allowed to have a systematic construction of hydrodynamic theories of a coarse grain for vortices. But these constructions so far, they have been done around thermal equilibrium, in which vortices do not interact, and there's no vortex annihilation, and we want to basically make a step beyond these constructions. So in this work, we saw that we can apply a theory of relaxed hydrodynamics around a non-equilibrium state. And we saw that this is a good description of our system by comparing it to holographic numerics. Okay, this is like a very short motivation, but since holography is not in the title of this program, let me just spend a few minutes introducing the basic ideas. So holography is basically a duality between strongly coupled QFTs and weakly coupled gravitational theories in one dimension higher. It can be formulated mathematically as an equality of partition functions and subject to certain boundary conditions at infinity. In particular, we can take, for example, empty ADS spacetime. And the most important entry in the holographic dictionary is the near boundary expansion of fields in this spacetime. The idea is that the leading independent piece of the field corresponds to a source in the dual quantum field theory, and the subleading piece corresponds to the VEV of an operator. Very quickly, I will just also flash some other entries in this holographic dictionary. So, for example, gauge symmetries in the gravitational theory correspond to global symmetries in the QFT. Each bulk field in the gravitational theory has a corresponding boundary operator. For example, the metric corresponds to the stress energy tensor. A U1 gauge field corresponds to a conserved U1 current. And some scalar field in the bulk can correspond to a scalar operator.
Is it a description of an arbitrary system or assumes very special state?
So I will be working in a regime where gravity is classical and the quantum field theory is strongly coupled. But in theory, many states of the QFT can have a smooth gravitational dual. So the states that we will be interested in, for example, thermal states, they do have gravitational. I think, the duality, basically, its strong version says that, the theories are absolutely equivalent. So like any state has a corresponding state, but we don't know how to describe it very well in this recipe. Okay, so as I said before, the leading boundary behavior of these fields correspond to sources in the QFT, and the subleading behavior correspond to VEVs of operators. Some examples of states, as I discussed, is that a pure ADS spacetime corresponds to the vacuum state of the quantum field theory. Whereas if we have a black hole with a certain Hawking temperature and a certain chemical potential, then this corresponds to a thermal state in the quantum field theory with the same temperature and at a charge density which is determined by the chemical potential. So we can gain some intuition also from the fact that the boundary physics in gravity correspond to UV physics in the quantum field theory, and the horizon physics in gravity correspond to the IR of the quantum field theory. And the quasi-normal modes in the bulk correspond to poles of Green's functions. Okay, this is just some entries in the dictionary. But let me now move on and describe the specific model that we're going to use. So we want to have a superfluid QFT. So we take a Maxwell theory in the bulk. It has a gauge field coupled to a complex scalar, which will play the role of the order parameter in our QFT. We will be in the probe limit, so will not allow for temperature fluctuations. This is just for simplicity. There's no conceptual reason not to do it. But that means that we will work around a fixed Schwarzschild ADS background. We will be in 3 2+1 dimensions in the boundary theory, so in 4 bulk dimensions. Yeah, this is just the metric of the black hole. We choose units in which temperature is just a pure number, and everything will be measured in units of the temperature. And okay, in general, the 2 probe fields that we will be concerned with is the gauge field and the scalar. From the boundary expansions of these fields, we can read the source and VEV for the U1 current, and the source and VEV for the scalar operator. Note here that I have set the source of the scalar field to 0 because we want to consider spontaneous symmetry breaking. So we don't.
What's the conserved charge for the maximum field?
I have set it to 1 as well. So there's a parameter.
Okay, to me, the word superfluid means that it's a charge neutral system in the Maxwellian sense.
Okay, there's a global U1 symmetry which is spontaneously broken. There's no gauge symmetry, if this is what you mean.
Here, the confusion is that the gauge symmetry is in the bulk space-time. But when you project it out to the boundary, this bulk gauge symmetry becomes just a global U1 symmetry. So you don't have electromagnetism, you just have a constant current, constant charge.
Okay.
Exactly. So this is a gauge field in the bulk, and this gives rise to a conserved current in the boundary. But we set the source of the scalar field to 0 because we want to have a spontaneous symmetry. And from these expansions, we can read off the QFT chemical potential and superfluid velocity by forming the usual gauge invariant combinations. Okay, so this is a holographic superfluid in a nutshell. We can indeed numerically find a homogeneous solution which has some spatially constant but only radially varying profiles for the fields. And in particular, I take the non-zero fields to be 80, corresponding to a chemical potential or a charge density. AI corresponds to a background superfluid velocity, and a VEV for the order parameter. And now we want to create a state which has vortices. So we solve the bulk equations of motion with certain initial conditions, which are the ones shown here. So we take the scalar field and we deform it by introducing randomly Gaussian defects in the field. So the positions xn and yn, they are randomly distributed in the system. Here at the bottom, I have written like the specific parameters for our simulation. The important thing is that we take an equal number of vortices and anti-vortices, so we have 0 net vorticity. And we want to have a large number of vortices. In total, we have 400 of them.
Your vortices, are there lines?
Are they, sorry?
If you are in 3G, yes, 3 plus 1,
Yeah.
then your vortices must be lines.
Exactly.
Then you have the oscillations of the vortex line somehow. Is it taken into account or it is like a rigid straight line?
Here I'm only considering 2 special dimensions. Here I only consider 2 special dimensions.
In some moment in the beginning you mentioned 4 dimensions.
Okay, yeah. So it's 2 plus 1 in the bulk, 2 special plus 1 time. In the boundary, and in the bulk is 1 more because we have a next.
And they are compensated, yes? So the total vorticity is 0. The vortices.
So here the special directions are periodic.
So the total vorticity is 0.
Yeah, exactly. We have equal number of vortices and anti-vortices. This is what the minus plus sign there is supposed to demonstrate. In higher dimensions, they are vortex lines, and I think there have been some numerics done in that case as well. but here for simplicity, I'm only in two spatial dimensions. Okay, I will just show you now a video of one simulation. So we can see here the vortex forming and annihilating. So sorry, this is a video of the orthoparameter of the charge density. I mean, and we can see the vortices moving. And at certain points, there are collisions between a vortex and an anti-vortex, and they annihilate, and the system relaxes. So this, yeah.
Is there an interaction potential between the vortices and the anti-vortices?
I'm agnostic about that. So I'm just putting these initial conditions. I'm solving the gravitational theory here.
Okay, even if you're agnostic, do you know the answer?
No.
Okay.
It's like it's a universal.
In the real world, there would be an interaction.
Yeah, but I don't know the microscopics of the dual quantum field theory.
And if they're just U1 vortices in 2 dimensions, it's straightforward.
Okay. Maybe I don't know if this presupposes that the coupling is weak. It's a weakly coupled QFT. What we're describing, because I don't know how to do it in strongly coupled QFTs.
Okay.
You're probably correct that when there are only few vortices left, then you could just look at a pair of them and resolve something like an interaction between them. But in these more initial states, where there are many of them, then this single vortex description likely does not apply because there's some collective motion of the whole vortex fluid. And so you can't really apply some kind of single vortex intuition to that state.
Yes, but you can apply a pair vortex intuition, which is correct.
You can apply what?
If you have vortices of opposite sign,
yes,
and they're both U1 in 2 dimensions, you can.
But I mean, if Vaios plays the start of the movie again, you'll see that it's really hard to actually isolate individual pairs.
Yeah.
They don't exist for any long period of time, these pairs.
Okay, very interesting.
Okay, so however, we can say something about like very wasn't interaction. Before going there, let me just tell you that we ran this simulation many times with many different initial conditions, and everything that I'll show you from now on will be for the averaged quantities. And here, for example, I show you the absolute value of the charge density and the superfluid velocity for the first and second lowest Fourier modes. So because we are in a box, the Fourier modes are discrete. And this is just to show how better the simulation becomes with increasing the number of runs. For example, you can see that with one run, the absolute value just oscillates very widely, but with more and more runs, it becomes like better behaved. But even with 8 runs, you can see that there are certain non-monotonicities in the absolute value which disappear for enough simulations. Okay. So, as we saw in the movie we just discussed, basically the interaction is pairwise vortex-anti-vortex annihilation. This basically motivates some phenomenological equation for the total number of vortices, which is a differential equation of the form shown there. And it leads to a time profile for the total number of vortices. And indeed, we can see numerically that this analytic behavior matches very well with the total number of vortices in our simulation. So basically, we run the simulations from having about 400 vortices up to like 20 or something. Okay, mobile vortices relax superfluid velocity. Okay, so we also have an equation for the average superfluid velocity decay, which looks like this. I can motivate in a little bit why it has the specific form, but basically the superfluid decay is proportional to the total number of vortices. in our sample. We can numerically find the value of the specific parameters, and we can actually see that the vortex decay is basically much smaller than the temperature of the system. So this basically tells us that there's some kind of adiabatic evolution where the macroscopic timescales are very much separated from the macroscopic timescale of the vortex relaxation. Okay, since I don't have much time, I will just move very quickly to hydrodynamics. So the system is described by two parameters, the charge density and the superfluid velocity. These are the lower energy modes. In the presence of vortices, we have some rotational part for the superfluid velocity, and we can define the net vorticity as just the rotational part. This is the number of plus vortices, of vortices minus anti-vortices. So the equations of motion that we're going to use is charge conservation and the Josephson relation. So usually there's no right-hand side, but based on the previous definition of vorticity, we can see that basically there's the vortex current entering on the right-hand side of the Josephson relation, and we also have finite temperature dissipative corrections denoted by chi tilde. From this equation, we can actually see that the vortex current conservation is conserved for the total net vorticity. It's always zero in our case. So by an entropy current analysis, we can actually find constitutive relations for all these currents here. And we can see in particular a coefficient which is sigma v. And this, if you substitute back in the Josephson relation, this leads to effectively the same equation that we saw before from holography for the decay of the superfluid velocity. Okay, here we just have some general words about hydrodynamics around a time-dependent background state. So since the superfluid velocity is relaxed and decays, it means that the state is time-dependent. And so all thermodynamic and hydrodynamic parameters of our system depend on the background superfluid velocity. And in general, the equations of motion take the form that is shown there with time-dependent coefficients, and there's no analytic solution for that. However, this is the final point. We can actually extract numerically these parameters from holography, the susceptibilities and transfer coefficients, and we can evolve these hydrodynamic equations. And then we can compare with the currents that we read off from the boundary from the gravitational side. I'll just skip this slide, it's not very interesting. But here I'm showing the comparison between the lowest and the second lowest hydrodynamic mode. So with black, it's just the exact holographic computation, and with blue, we saw the evolution of the hydrodynamic equations. We see good agreement, especially for the lowest mode. Again, certain non-monotonicities in the black line are probably due to the low number of runs, but yeah, we expect them to behave even better with more runs. Okay, and so we see that basically this relaxed hydrodynamic description describes well the holographic data. And just very quickly, I will flash that based on the numerical evolution of the transport quantities, we can actually introduce a perturbative scheme, and we can solve, we can have an analytic solution for the time-dependent dispersion relation of the two modes, and they look like relaxed hydrodynamic modes, superfluid hydrodynamic modes. So the first part is the usual superfluid velocity at finite superfluid velocity, and the second there is just a gap for this mode. Okay, let me just finish with some open questions. I have 1 minute. Okay, so this is an overview of what we've done, and there are still some open questions that we want to explore, which is, first of all, what's the relation of this system to a non-thermal fixed point? We can also do numerics, as Blaise said, for a small number of vortices, and we can actually check if there's a hydrodynamic description in this case. And it's also interesting to consider also states with a finite net vorticity. Thank you. And that's all I have to say. Thank you.
Any questions?
Can you trace your experiment, your modeling down to complete or almost complete annihilation of vortices? Because when you show it, looks like your density is almost the same.
Yeah. So in this hydrodynamics that we set up, we basically assumed a coarse grain vortex density.
No, I understand, but when you showed the modeling, you showed individual pictures, you showed individual vortices, yes?
Yeah. So we expect the hydrodynamic description to break down at some point when there are really a very small number of vortices.
I think the question is whether we can run the numerics all the way to the state where no vortices are left.
Yeah.
And in principle, yes, then it's all a matter of keeping the numeric stable for such a long time. But there's no obstruction in principle.
It will be very good if you can color your vortices as positive and negative here.
Yeah, that's true.
It will be interesting to see correlations. And
that's always an equal number. But this hydrodynamic description, we expect it to break down at some point when there are few enough vortices.
So in the fascinating talk, thank you very much. So in the hydrodynamic averaged over vortices description, does the equivalent of second viscosity appear between the gradient of the ground state phase theta and the entropic degrees of freedom?
So the
second viscosity. So in real superfluids like this, there's another term in the hydrodynamics, which is the second viscosity that links the broken symmetry ground state and any entropic excitations in the system.
Oh, okay. In general, yes, and we can write down such a...
Is it in that beautiful set of equations or?
No,
okay.
Because here we're considering the probe limit.
Okay.
So we are freezing entropy fluctuations.
So for superfluid people, predicting the second viscosity is a very serious problem. It's never been done a priori.
We're actually working on that as well. So.
Okay, cool. Oh, sorry, and can you reach the Berezynski-Kosterlitz-Stalos point in your model? You're at a very low temperature in this model. So if you would go up in temperature, would you reach the BKT point?
No, but it's changed. Vortices have been injected. It's changed model. It's not.
But it's a thermal equilibrium model. It should generate more vortices at high temperatures.
Yeah. I don't know the numerics.
Okay.
Because this is a large N system.
Yeah, I understand.
Fluctuations are suppressed, and so you never can see the actual BKT.
But this is a finite temperature model.
Right, but the fluctuations that lead to BKT are suppressed by 1/n. So when you work at strictly large N, you don't see these.
I see.
So unfortunately, it's all the transition itself that these models are capturing is always mean field.
Any other questions? If not, let's thank the speaker again.